right, so derivatives, of course, but we're looking specifically today as how to determine where they fail to exist, because believe it or not, you will not be able to find the derivative of everything. There's Lindsay. So, first and foremost, okay. So in our last unit, we were exposed to the word differentiable. And we knew at that exact moment in time that, when we saw the phrase differentiable, we knew that that implied that the function was continuous. So obviously that is still true, but we are going to just add a little bit to this idea now. What does it mean to be differentiable? So to be differentiable at a point implies that you can find the derivative, which of course we know is the slope of the tangent line, otherwise known as the instantaneous rate of change, at that particular point. Okay? So again, differentiable is just a way of saying something has a derivative. So take a moment, jot that definition down, and we'll move on from there. So again, to be differentiable implies that you can find the derivative, aka the slope of the tangent line, at that particular point, or at a point. So as we jump into this idea, I want to take that brief moment. You've already gotten this written down 500 million places, but I like to make sure that we review the idea of continuity. So we know for a function to be continuous at a point, the following three conditions have to be satisfied. The value itself at that point has to be defined, the limit has to exist, and tying it all together, the limit has to exist and the defined value have to equal the same value. So always want to keep that in mind and coming back to that thing. So I wrote this down twice. Now I'm like going, I should have reviewed my slides. So yes, the derivative of a function at a given point is the slope of the tangent line at that point, aka the instantaneous rate of change at that point. So again, we know derivative. We now know what it means. And I again want to just keep emphasizing that you understand that whole piece and that portion. So a derivative equals the slope of a tangent line. Which is equal to the instantaneous rate of change. So we're going to take those two ideas, continuity and what it means to be a derivative, and put them together in order to be able to decide when is something able to be differentiated. So a little bit of common sense. If you can't draw a tangent line, then you don't have a derivative. So it would be clear, or should make assumptions, that any discontinuity would mean no derivative. So situation one, and there are three of them. So limits fail to exist at any points of discontinuity. So you know our three types of discontinuity. Our very first one, of course, is our removable discontinuity. Their derivative does not exist at x equals 3 because we are not continuous at the value of x is equal to 3. Then we have our non-removable. This would be our jump discontinuity. This would be infinite discontinuity. And obviously, at x equals 3 in both of those values. No derivative at x equals 3 because the function is not continuous at x equals 3. So, limits fail to exist at any point of discontinuity. So if you see this, be mindful and be like, sorry, can't find a derivative because I can't find the slope of the tangent line at that given point on functions that are not continuous. If I roll through these way too fast, you know I'm recording it and then going to post this as well too, but if you need me to slow down because you're writing, by all means, give me a quick shout out. So does this mean that all continuous functions have derivatives? And the answer to that question is no. So a lot of people confuse the idea in saying that if they assume if something's continuous, it must have a derivative. So continuity itself is a necessary condition for differentiability, but it's not a sufficient condition. So if you're differentiable, you can assume you're continuous, but if you're continuous, you cannot assume that you're differentiable. Because then that takes us to situation number 2. So derivatives fail to exist when there is a sharp corner, or otherwise known as a cusp. So we can see in this function, and I'm just going to call this, we'll call this A, point A. I know the function's continuous because the limit as x approaches A from the left of this function is equal to the limit as x approaches A from the right of this function. So therefore, we are continuous. And this whole idea of making sure our left-hand side and right-hand side still is important, even when we're talking about derivatives. So if I'm looking at this in terms of my derivatives, I want to know what's my limit as x approaches A from the left, make sure I get this function right, of f of x minus f of A all over x minus A, again from the left, is not going to equal the limit as x approaches A from the right of that slope. Their slopes have to be equal in order for this to work. So our limit, which of course we know is our slopes, if you take a look at this, it's kind of obvious that the slope of this line is going to be a very sharp, steep, positive curve, whereas the slope of this line is going to be an equally steep negative value. And if your slope coming from the left does not equal the slope that is coming from the right, you're not going to be able to have a derivative at that point. Because again, a derivative is based on the idea of a limit. And we know in order for limits to exist, the limit from the left has to equal the limit coming from the right. And that implies and also goes to derivatives. So therefore, not differentiable. Now you're not going to be asked to prove this. When we get into some piecewise functions, we get to do a little bit more work to figure some things out in regards to this. But as long as you're able to look at a graph and be able to identify that you are not differentiable at that point, you're usually in a pretty good place. So look for those sharp turns or those cusps. And I've said it, but let's make sure we write it. So differentiability guarantees continuity, but continuity does not guarantee differentiability. So now when we say a function is differentiable, and they usually will give you an interval, it means that you can find the derivative at any given point in that interval or in that domain. And then that leads us to our last one. And this one rarely comes up, but every once in a while they'll give you a graph. And in the description of the graph, they throw this in. And it's like, as long as you are able to pick up on it, you've got yourself a sense of what's going on. So the last situation where a limit will fail to exist is when the function has a vertical tangent line. And you know when you have a vertical tangent line, that means that if you had your slope and you did your slope of this line, you would have some sort of left-right value. Your rise value would be some number, but your denominator would be 0 because you would not be moving to the left or to the right. So we can't have an undefined value. It's an undefined value, an undefined slope. We can't have an undefined slope as a tangent line. So you're often told, and I can't even give you an example of a direct function that has that vertical tangent line, but if there is a vertical tangent present, it will be told to you. But it's one of these things, again, I've seen it on a free response problem here and there, where they'll throw in, oh, there is a vertical tangent at blah, blah, blah. And you just have to pick up on that and understand, oh, that means we're not able to find a derivative. The function is continuous again, but it's not differentiable at that point where the tangent line goes vertical. And that's probably the shortest lesson I've ever done for you. So I'm going to pause.